In this last video about exponential growth and decay, we're going to talk about an example of exponential decay, even though it can be used in an exponential growth situation. And the situation is this: we've all seen things that we take, let's say, something hot out of the oven and we allow it to cool. This Newton's law of cooling applies to that. So in the example that we're referring to here, it says, suppose that you left a cup of soup and it cools to the temperature of the surrounding air, or a hot silver ingot piece of metal is immersed in water, it cools to the temperature of the surrounding water. In these situations, and this is where we got to read this carefully, in these situations, the rate at which an object's temperature is changing at any given time is roughly proportional to the difference between its temperature and the temperature of the surrounding medium. So in a vein similar to this, dy dt is equal to k times y, we're basically going to say the differential or the derivative, or the rate of change of the temperature and minus the surrounding temperature with respect to time is proportional to the difference between the temperature and the surrounding temperature. And we're going to throw a negative in there because we have decay here. And if we find this k value, we're going to find that it's going to be positive if it's decay and negative if it's growth. So we now have a separable differential equation, and we are taking the derivative of the difference in temperature with respect to time, and we're separating that into dt minus ts over t minus ts. So our variable t minus ts is in the denominator, and that's equal to negative k dt. And we can go through and we can solve this, and if we were to integrate both sides, basically what we're going to get is we're going to get the natural log of the absolute value of the difference in temperatures, and the surrounding temperature is equal to e to the negative kt plus some constant c. And then we would write that as e to the negative kt times e to the c. And since we're going to be talking about cooling, the difference, T minus Ts, T being the temperature of the object and Ts being the temperature of the surrounding, we don't have to worry about the absolute value because that difference is going to be positive. And what we would find out is if we were to solve for that constant out in front, e to the c, that's going to turn out to be the initial temperature of the object minus the temperature of the surroundings. So basically we end up with the following relationship. The difference in the temperature and the surrounding at any given time is equal to the initial temperature minus the temperature of the surroundings times e to the negative kt. And if you want the temperature of the object at any given time, we would solve for t and just add Ts to both sides. So we have the initial temperature minus the surrounding temperature times e to the negative kt plus the surrounding temperature. If you think about this equation, basically what you're looking at is the first part being an exponential decay and the second part being a vertical shift upward of whatever the surrounding temperature is. So basically, if you're looking at this on a graph, you'd have a horizontal asymptote at the surrounding temperature, and over time, the temperature would eventually decay to that temperature. If it were a heating situation, then you'd have a situation where the temperature would eventually rise to that temperature. We're going to stick strictly with the cooling situations. So here's an example. A hard-boiled egg at 98 degrees C is put in a pan under running 18 degrees C water to cool. After 5 minutes, the egg's temperature is found to be 38 degrees C. How much longer will it take the egg to reach 20 degrees C? So we're going to use the left-hand side of the form of the equation because we're not searching for a final temperature, we're searching for a time that it takes to reach a particular final temperature. So our setup is going to be something like this. The final temperature minus the surrounding temperature, which is 18 degrees Celsius, is equal to the initial temperature, 98, minus the surrounding temperature, which is going to be 18, is equal to e to the negative kt. Alright, so as you can tell, we have a few variables in there. Don't forget, e is not a variable. So what we're going to do is we're going to use the temperature at time 5 minutes to solve for k, and then we're going to figure out how much longer it will take the temperature to drop to 20 degrees C. Alright, so how do we do this? Well, we know that 38 is going to take the place of t minus 18 is equal to 98 minus 18, which happens to be 80, times e to the negative 5k, because at time 5 we know that t is 5. So we have 20 is equal to 80 e to the negative 5k, and we're going to solve that equation for k, divide both sides by 80. So we get 20 over 80, which is 1/4, is equal to e to the negative 5k. To solve that, we're going to take the natural log of both sides. So natural log of 1/4 is equal to negative 5k, and k is equal to negative 1/5 natural log of 1/4. So you could leave k in this form, or if you wanted to, you could recognize that natural log of 1/4 is equivalent to natural log of 1 minus the natural log of 4. So we basically have negative 1/5 times natural log of 1 minus natural log of 4 is equal to k, but natural log of 1 is 0, and the negatives cancel out, so we basically get k is equal to 1/5, or 0.2 natural log of 4. Now we want to go back to our equation, and we want to see if we plug 20 in for t, how long extra will it take for the temperature to drop to that? So 20 minus the initial, or the temperature of the surroundings, is equal to 98 minus 18 e to the 0.2, negative 0.2 natural log of 4t. So 20 minus 18 is going to be 2. 98 minus 18 is 80. E to the negative 0.2 ln of 4t. And we're going to divide both sides by 80. So 2 over 80, or 1 over 40, is equal to e to the negative 0.2 ln of 4t. At this point, we're going to turn to the calculator to help us solve this equation. And we could use either of these two equations to solve. I picked the second one because I wanted to illustrate something. Even though it can happen, we can see that with the first. So I put the left side of the equation in and the right side. And I'm going to start out with a zoom standard. So if we hit zoom standard, zoom 6, there's my exponential decay, and I'm wanting it to get down to 1/40th, and 1/40th is very close to y equals 0. So you're having a hard time seeing where they intersect. But if you use the intersect function on the calculator, number 5, we should be able to find where they intersect if they intersect within the window that we have. So notice I got this error. It said no sign change. That's basically how the calculator finds it, which tells me that either I made a mistake or my window is not big enough. So what I'm going to do is I'm going to quit. I'm going to go back to my window, and I'm just going to make X max bigger. I'll go up to 20. Just a guess on my part. I'm going to graph it again, and I'm going to use the intersect function again. So second and the trace and the intersect function one more time, and hopefully our point of intersection is within our window. So 13.305. And one other thing I wanted to point out about this is that this is the time at which 13.305 at which the temperature of the boiled egg reaches 20 degrees C. So the answer is based on the question, how much longer will it take the egg to reach 20 degrees C? Well, after the first 5 seconds, it dropped to 38 degrees C. So our answer is going to be 13.305 minus 5 seconds. So we have an answer of 8.305 seconds. And as I was just checking my answers, I realized that I used the wrong units here, so that would be 8.305 minutes. And if they had asked for the units on the AP exam, I would have lost points on that. So pay attention to the units.